Awesome. And I'm gonna go ahead and share my screen. So yeah, hi everyone. Thanks for joining today. Welcome to Multimodal Weekly, hosted by 12 Apps. We've been meeting on a weekly basis over the past 2 years or so. This is our virtual webinar series that serving mainly purpose to educating practitioners about the field of multimodal AI and video understanding. Here are the topics that we tend to cover on a weekly basis. Research, right? New research that coming out from the domain of multimodal AI and foundation models. And oftentimes we also have like developers, engineers, founders to talk about application of multimodal in different verticals. We have a Discord community where I sometimes invite team members to share their projects. And finally, we have internal team members talk about how to use our platform and API. In some of the more recent session, we'll be focused a lot more on the research side of things. So you can see here some examples, topic that was presented in this session. So we have everything ranging from like the retrieval side of things to obviously benchmarking dataset to deep dive on, video reasoning, encodings, video encoders, etc. So today, super excited to have three presentations. All of them actually from UNC Chapel Hill. First one is going to be Zhang, who currently, he's a PhD student at Chapel Hill. He will be able to talk about a work called LLoVi, which is a simple yet effective large language model framework for long-range video question answering. And secondly, we'll have Emon Islam, who will talk about, I think, a pretty new work called BIMBA, a selective-scan compression algorithms for long-range video question answering. And finally, we'll to close the webinar, we'll have Shoubin Yu, who will present another work called CREMA, which is a generalizable, highly efficient, and modular modality-fusion framework that can incorporate any new modalities to enhance video reasoning. So all three of the speakers come from Chapel Hill, and I know, I think the lab has been pretty closely in collaboration with 12 labs. So yes, we're excited for this session and learn more about, from the research point of view, what are the things that they're working on in the context of video language model. Just a quick slide on the logistical note. So for the attendees, feel free to send question on the Zoom chat as you listen to the speakers. And after each of the speaking slot, we'll have a short 5 minutes Q&A interactive where you can ask questions to the speaker after they finish. So with that, I'll stop sharing my screen and see, how about you? Let me enable screen sharing first.
Sure, no problem.
Yep, now you should be able to share your screen and go ahead.
Cool. Thank you, James. So let me share my screen. So
Yep, I can see it.
cool. So hi everyone. My name is Zhang. I'm a second year PhD student at UNC Chapel Hill, working with Professor Geddes Portasius, and I'm mainly interested in video understanding, multimodal learning. So today I'll present my work, a simple LLM framework for long-range video question answering. And this work has been accepted by EMLP 2024. Cool. So first, I'll start with the motivation of our work. So firstly, the most existing video models only focus on short videos. So if we apply like long videos on video models that are designed for short videos, then obviously the performance will drop a lot. Also for long video understanding models, so many models use like a very complex design, like for example, memory queue or state space models. And those complex designs usually make such models hard to reproduce. And we are thinking about, can we design a simple framework which is also able to deal with long video understanding questions. So also recently we can see that large language models have shown very impressive long-range reasoning abilities. For example, the long document understanding, long horizon planning tasks, etc. So in our project, we actually want to leverage the LLM to build a very simple, a training-free, and also very effective model for long video understanding. So this is our overall framework. So it's a very simple framework called LLoVi, LLM-based framework for long-range video QA. So as you can see from the figure, so basically the LLoVi framework consists of two stages. The first stage is just to sample short clips from the long video and extract captions from each clip. And you can see from this figure, this is a 3-minute long video. For example, we can split this very long video into multiple 1-second short clips. Then we just use a pre-trained captioner to extract the caption of each clip. So we can see from this figure, for example, the first caption is "C chops tomatoes on the cutting board." The captions are usually very short, but they can usually capture what the person is doing in the video. So that is our first stage. So in our second stage, we just input all the captions and the question into the LLM and prompt the LLM to answer the given question. For example, for this video, we have the question, what was the order and organization of these actions in the video? And the LLM will just give the correct answer based on the captions instead of the raw videos. So yeah, this is our framework. And within our framework, we also designed a, a prompting technique to improve the question answering accuracy. We call that multi-round summarization prompt. So in this prompt, in the first round, we will prompt the LLM to summarize the raw captions. So, for example, in this figure, we can see the raw captions. If the video is, for example, 108 seconds long, we will have 180 captions, right? So we just input all the captions to the LLM and ask the LLM to give us a short summary of the raw captions. And optionally, we can also input the questions we want the LLM to answer here, because after input the question, the LLM might be able to give us more accurate summary tailored to that question. So that is the first round. And in the second round, we will prompt the LLM to answer the given question based on the summary instead of the raw captions. So our intuition for this multi-round summarization prompt is that the raw captions can be very, very long, and there are very much repetitive information inside the raw captions. And actually, LLMs are very easily distracted by repetitive informations and those distractions in the raw caption. So our hypothesis is that after we get the summary is much cleaner and more coherent, and I'm sorry. The summary is much cleaner, is very coherent, and maybe is even tailored to the given question. So if we input the summary to the LLM instead of the raw captions, maybe we can get better results in question answering. So that's our intuition for this prompt. Yeah, basically, the we have the framework and we have this prompt. That is our method, and we evaluate our method very thoroughly on many data sets. So one of the data set is called EgoSchema. It's a very long form video question answering data set. So it contains 5,000 multiple question QA pairs, and the average duration of each video is 3 minutes. And unlike many previous long-range video QA benchmarks, this EgoSchema benchmark actually requires analyzing the visual cues from the full video to answer a given question. Because what happens in many prior data sets is that even the video is very long, the model does not need a strong temporal reasoning ability to understand the model. So maybe the model just need to look at a few frames one or two frames, then it's able to answer the question. But this is not happening in this EgoSchema dataset. We can see one example from here. So, for example, the question is like, what is the overarching behavior of C and the man in the video? And we can imagine to answer this question, basically each frame count. The model needs to really take a look at many frames and do temporal reasoning of the video to answer this question. So this is the main data set we use. And here is the result of our method on this EgoSchema data set. So firstly, from this table, we can see that our method LLoVi outperforms previous SOTA method by a significant margin, which is 3.9%. And then we can compare our method with prime method, which are also LLM-based methods. And we find that in this throughput metric, so our method is 2 times higher than prior method, which means that our method is 2 times faster. And we can also find that if we use the multi-round summarization prompt, that actually gives us a very huge performance, which is 9.4%. So this shows the effectiveness of our multi-round summarization prompt. We also did a lot of empirical study on a subset of EgoSchema, and the first one is the ablations on the visual captioner. So here we compare like a 4 visual captioners: EgoVLP, Lava, Blade 2, and Lavilla. And here are the performance. We can see that Lavilla as the visual captioner gave us the best performance. So this is probably because Lavilla is specifically designed for egocentric videos, and EgoSchema is also egocentric videos. That's one reason. And we also include this result called Oracle Captioner. This is because the EgoSchema dataset is from the Ego40 dataset, which contains manually labeled narrations. So for this Oracle Captioner, we just use the human labeled narrations as ground truth captioner, and input the ground truth captions to our model and compute the performance. We can see that this Oracle baseline outperforms all previous visual captioners. This also shows that there is still a room for current visual captioners to improve. So we also see that the better captioners we have, the better performance our framework LLoVi will have. That is actually a very nice property. So in the future, we imagine there will be more powerful visual captioners, and with more powerful captioners, the performance of our frame also increase. And we also do ablations on different large language models. So we tried Mistral, Llama 3, 8 billion, 17 billion, and we tried GPT 3.5 and GPT-4. And we found that GPT-4 as the LLM gave us the best performance. So we also explored like the video processing configurations. So this table shows that because the first stage of our framework, we need to dividing the long videos into multiple short clips. This table explores the best length of the clip. So we can see that if we divide the long video into multiple 1 second clip, that will give us the best performance. And if we increase the clip length, the performance will drop a little bit, but still decent results there. So this table explores how do we sample the short clip. For example, after we divide the long video into multiple 1 second short clips, how do you sample it? Like one naive way is to just use all of the clips. And optionally, we can also, for example, sample one clip every 2 clips. We can also sample one clip every 4 clips, which is this 1 divided by 4 setting in the table. And from this table, we can show that the naive setting, in which we use all the short clips, give us the best performance. However, but even if we sample one clip every 8 clips, which is this 1 divided by 8 setting in our table, we can see that the performance only drops a little bit. But the sparse sampling gives us another benefit, which is which is like we will not need the input of the LLM will not contain so many captions, so that is very efficient. And also when you try to extract the captions from the captioners, so that also costs a lot of time. If we can reduce the number of clips, that is a very good thing for efficiency. So we also explored the variations of our proposed multi-round summarization prompt. So basically, the C to S variant means that during the summarization, we only feed the LLM with the raw captions. The CQ to S means that during the summarization, we also input the questions. We believe that inputting the question might be able to guide the direction of summarization of LLM, which can be beneficial. And from the table, we can see that, yeah, it's true that the CQ to S variant give us the best performance. Yeah, so here we compare our multi-round summarization prompt with other prompting techniques like chain of thought and solve, and we found that our prompt is the best among all other prompts. So that is our main results on EgoSchema. So we also tried other data sets, the NExT-GQA data set and the Interleaved data set, and yeah, our we can see that our LLoVi framework outperforms prior SOTA method. We also tried like a NExT-GQA dataset. So this dataset also requires the model to temporarily ground the question to the video. So basically, the model needs to output which frames are related to the given question. And we found that even in this benchmark, our framework performs very, very well. So yeah, to summarize our work, we present LLoVi, a very simple, training-free, and effective LLM-based framework for long-range video QA. And LLoVi achieved very strong results on multiple benchmarks. And we also did a very thorough empirical study on various design choices of our approach. Okay, that's all my presentation. Thank you for listening. And if you have any questions, you can ask me here.
Awesome. Yeah. Thanks a lot, C. So yeah, if any question from the other audience, please either unmute or you can put on the chat. Maybe just to get started, one other thing that you mentioned about limitation is that existing visual captioners suffer from hallucinations, and they often also like struggle to effectively capture fine-grained visual details, right? And you also said like in the future with more powerful visual captioners, then this technique can be even like better, right? So just curious, what are some of the like most promising visual captioners that you're seeing in academia right now that you think you might want to incorporate in the future?
Yeah, that's actually a good point. And also, I also want to add in another point. It's like you can see that this is just a naive captioner. It only accepts the current frame. But in the future, I think we can even try like input the question to the captioner, and that will give us more details about that question, which might lead to better results, right? And in terms of the current best visual captioners, I don't have a I think GPT-4V is pretty decent as a good captioner, but our paper, uh, but our paper is actually uh, even before the GPT-V came out, so we didn't try
Mhm.
it. So yeah, I would imagine if you use GPT-4V uh, in our framework, almost certain you can get like a much higher performance.
Yeah. And you also mentioned another limitation of the approach is that many modern large language models are not designed for long context modeling,
Yeah,
which,
that's
which is
true.
which is important for this task of long range video question answering.
Mhm.
So just out of curiosity, like what could be like a better design of LLM to improve performance for long range video question answering?
Yeah, that's a good point because actually there is already a few works building on top of our framework. So our framework is very straightforward, just a very straightforward summary to the LLM to increase the performance. But actually, recent work also explores um, keyframe selection. So, for example, to answer one question, you do not need really all the frames. So is there a good way to locate the frame first? Then you just extract the captions of the keyframe. Then you input the captions of a keyframe to the LLM. That will very effectively reduce uh, the text, the number of words, the input text of the LLM. And actually, those those works, the performance are much higher than our LLoVi framework. I think that's a very interesting direction.
Awesome.
Yeah.
Well, I think that's all the question that I have related to this work. Um, are there any other exciting work like that you do currently working on right now that
Uh, it-
you know uh,
it-
on video understanding, this kind of thing?
yeah, that's a good point. Actually, we just speak of like the following up works of our LLoVi framework. Actually, our third speaker, Shoubin, is working on something very relevant. I think their publication video tree is recently accepted by CVPR, and that improves the LLoVi framework a lot. So if you are interested, you can check that paper video tree.
Nice.
Yeah.
Yeah, so excited to hear more about that later on.
Cool.
Well, thanks again, Caesar, for going first and present LLoVi.
Well,
Um, yeah, so let's go forward, continue, and go ahead with the second speaker. So yeah, Emon, do you wanna share your screen and go ahead? Or unmute yourself as well.
Uh, Thanks, James. Can you see my screen?
Yes, that's it.
Yeah. Hello, everyone. I am Mohaiminul. You can also call me Emon. I am a final year PhD student at UNC Chapel Hill, and I work mostly on video understanding and multimodal deep learning. And today I will present BIMBA, a selective scan compression for long range video question answering. I worked on this project last summer when I was a intern at Meta, and this is recently accepted by CVPR 2025. So uh, so motivation of this work is recently we have witnessed a lot of interest in multimodal large language models. However, while existing image LLMs, especially in academia, has shown great performance, but they existing video open source LLMs cannot perform very well, and they can only process like short videos. So in this work, our goal is to develop a efficient video MLLM that can process long-range videos and answer questions. Here is most existing open source LLMs, how they work. So given a video, and so first we divide each frames into some batches, and then we encode each frames in using a image encoder or a vision encoder, which results in these batch level tokens. And afterwards we pass these batch level tokens or features along with our question tokens to the LLM to generate the answer. However, the issues with this approach is that if we have a long video, this may result in a lot more tokens. For example, if we have a video of 100 frames and we divide each frames into 24 by 24 tokens, this can result in 57,600 tokens, which can be a lot computationally costly, especially for academia setup. And also, another thing is that many of these tokens are very redundant. So if we look at a long video, we see a lot of repetitive frames and also many redundant information. So our goal is like, how can we develop a efficient model that can process this long sequence of tokens and also extract key tokens and discard redundant information. So for this, we draw motivation from NLP and sequence modeling. A spatially structured state space sequence model. So this is a very efficient model recently proposed and a competitive model for transformer architecture. What it has, this has this like basic operation called state space modeling, which can be expressed by these two simple equation. So given a input sequence xt, xt, you can first apply the first equation to get a hidden state, which is a recurrent formulation, and then you can generate your output, which is the yt. So here x is the input sequence, h is the hidden state as in a RNN, and y is the output. So this model is very efficient compared to like self-attention or transformer models. So this invariant, so your parameters are constant for like all the time step of the input sequence, and it does not change based on your input timestamp. So there is also another improved version called S6 model, which has been used in Mamba LLMs. So here the improvement is that now the parameters B and C, this becomes input dependent. So, being a input dependent, you can now select your important information. So it can selectively progress or propagate or forget redundant information. So and also in the Mamba paper, it has been shown that these type of selective scan models are very effective at selective copying task. So here, this is a artificial tasks where given a long sequence, you need to only select these colored tokens. So you can see Mamba achieves very high performance compared to other efficient linear models. In this project, we ask ourselves question like, can we also use this kind of selective mechanism for videos? Because videos are also it has many redundant frames. Maybe we can also use this technique to select important frames or tokens from long video inputs. So how can we do that? First I will introduce the framework. So our framework is like given a long video and the frames. We divide each frames into a image encoder as like before, and then we utilize a selective-scan spatiotemporal token selector. So this token selector, it reduces the number of tokens a lot. So for example, 16 times, then this passes this compressed representation to the LLM along with your quotient tokens. Now using this compressed token, this becomes like very much computationally efficient. So let me describe the what is this spatiotemporal token selector. This is so for designing this spatiotemporal token selector, first given a long sequence of spatiotemporal tokens from image, we initialize some visual queries. So these visual queries are initialized by some pooling layers. So they give a but these visual queries are lot less than the input tokens. So this while pooling it provides a good initialization for visual queries, but it cannot capture the long range spatiotemporal dependencies because pooling is just a simple operation. So what we does is we append these visual queries with the spatiotemporal token and pass like this long sequence to our selective-scan token selector. So inside the token selector, we has a layer normalization, a input projection layer, which is just a linear layer, and the selective-scan layer motivated by Mamba. So even though this is a very long sequence, Mamba can efficiently model this long sequence and capture fine-grained details from these spatiotemporal tokens. So these fine-grained details extracted by Mambas are added as a residual connection on top of our like pooling features. Afterward, we only pass these visual queries to the LLM. So now we have this compressed representation of visual queries, which is orders of magnitude less than original space-time tokens, and it also contains both global properties and also fine-grained details captured by the selective-scan. So this is the overall model, and we also propose some video specific or our application specific modification. For example, like we found that if we add the visual queries at the end of the spatiotemporal sequence, that can result in positional bias because then the queries will be more influenced by the tokens from the later part of the sequence. This also is true for like if we add the queries to the beginning of the sequence. So what we propose is that we distribute these queries equidistantly throughout the visual sequence, and it turns out to be a better design. We also utilize like a bidirectional scan using the Mamba layers. So yeah, we first apply a forward scan and then this backward scan. So these are some modification that also helped us to design a effective model for long videos. So here is our experimental setup. So we train on our model on 370 100K instruction tuning data aggregated from like publicly available data set. And we also did not use any GPT-4 generated data like many of the competitor models. So our instruction tuning data is also very shorter. And also we evaluate on a wide array of benchmarks like MV bench, perception test, temp compass, and also video MME and ML view, while the earlier benchmarks are for short video QA, but later contains long videos like our long videos. And we also experiment with other baselines, for example, the vanilla baseline, which does not use any compression. The pooling baseline, this is just the simplest form of compression, where we used pooling to compress the physiotemporal tokens. We also use other two advanced like compression technique like self-attention based and perceiver, where we replace the selective scan layer of our model with the corresponding self-attention on perceiver layer, and we maintain the same compression ratio. So first, I will present the result on the comparison of the compression method. So here we can see in the x-axis we has the number of input tokens, and in the y-axis we have the accuracy for NExT-GQA and EgoSchema benchmark. So first we observe that for vanilla, which does not use any compression or self-attention models, they quickly go out of memory for high computation cost. The pooling, it cannot perform very well, and the performance degrades if we go for a long sequence. The perceiver maintains okay accuracy, but we can see that our compression technique like BIMBA, it achieves like much better accuracy, and it also improves the performance as we increase the number of input frames. So here is the computation cost analysis. So as we discussed, as we saw previously, like the vanilla or the self-attention model, they has very high memory and runtime because of the quadratic cost of the self-attention, and because of the high volume of space-time tokens for like vanilla models. On the other hand, the BIMBA model maintains lower computation cost, like it is slightly higher than pooling, but it is much less than like other compression techniques. So here is the comparison on the state-of-the-art result. So actually, so when we started the project, we experimented with like Vicuna, the lava model based on Vicuna backbone, because that was the state of the art back then. And we can see using this backbone and using the same training data, our model achieves like best performance. It also outperforms like all the other models using the same backbone on all of this, like in most of this benchmark. And we also experimented with Llama 3.2 backbone, which improves the performance a lot compared to like these old lava models, and it can even achieve like very good performance on a benchmark like EgoSchema, despite using significantly less instruction tuning data. But we can observe that still many of our performance is less than like some of the later model that came afterwards, based on QN2 backbone. And one of the advantage of our technique is that this is a plug-in-play module which you can apply to any like this kind of like LLM to achieve compression. For example, later we added our compression technique to a later lava model based on QN2, and you can see now we achieve state-of-the-art performance with benchmark like video MME or MLVU. So that's all for the quantitative results. So qualitatively, it can also generate like free-form question answer for videos, like describe the events in details for videos, even generate like high-level question like why the video is funny. It can also understand like egocentric or procedural videos and answer questions like what the man is cooking and what are the steps of the cooking the man is performing. So yeah, that's all. Thank you, everyone. Our we code and model will be released soon, and we will also present it in the CVP. Thank you.
Awesome. Yeah. Thanks, Emon. This is super new work, so I didn't file the paper, but yeah, I mean, I assume you're gonna publish it soon on archive and all that stuff, right?
Yeah.
And I remember Gedas actually presented this work at our workshop, like in the reps. He gave like a couple slides about it, so not too much detail. So it's great that you can talk in much more detail over here.
Yeah.
Can you go back to some of the slide on the architecture again? Is the architecture overview? Okay.
These are these. I guess it's just a overview. Maybe this one. Yeah.
I see. What is the LLM of choice here? You said Vicuna.
Yes, so it is Vicuna, but in the end we end up experimenting with like Vicuna Llama 3.2 and also like the QN2.
Oh, when? Yeah. What and which is the best
Yeah,
LLM that get the optimal performance?
I think QN is the best currently that and it's the also the most recent one. Like if we.
And the image encoder in this scenario, which is the encoder?
So that also depends on the like LLM. So we actually start from pre-trained pre-trained image based models. So for Vicuna, they use like clip like for that lava version. So we start from image pre-trained like a MLLM checkpoint and then instruction tune using video data. So for Vicuna based LLM, it was clip. For Llama, it was meta clip, and for QN, I think it's also clip. Yeah.
I see. Perfect. Great. So yeah, I think that's since we only have about 15 minutes left in the webinar session. I think we can probably push it to Shoubin to conclude the session. Thanks again, Emon, for going over this new work. Super excited to see it.
Yeah.
This CVPR soon.
All right, can you see the screen?
Yep.
Okay, thanks. So yeah, I'll start my turn, and thanks for the invitation. I'm happy to be here. And I'm Shoubin Yu. I'm the third-year PhD at the UNC Chapel Hill, work with Professor Mohaiminul, and I'm mainly work on the multimodal learning and many different video applications like video understanding, video generation, and video action, LLM for embodiment AI. So today I will present our new work CREMA. Its name is generalizable and efficient video language reasoning via multimodal modular fusion. And this work is done with our postdoc Zhang and Mohaiminul, which has been accepted in the iClear this year. So here I give a very high-level motivation because as we can notice, our human beings actually perceives different information modalities that beyond visual to assistive visual. For example, when we see the depth map of the video, we can use it to perceive the distance information. And when we are seeing some surface normalization, we can find the information about the object shape. And the touch map and the thermal map is actually help us to perceive some information that beyond visual to help us to make some decision. So actually our human beings are perceiving a many-modal work. But the problem is that how to transfer this ability to a model. So actually, this existing many challenges for this to integrating multiple modalities within a unified framework with with very limited data, limited training resources. Like we have like some standard modality like image, video, audio, text, which is very common. But in the real world, we actually have other like real modalities like optical flow, depth map, thermal heat map, 3D point cloud, like clinical data, genetic data, and surface normalization. So first, how can we design a framework to perceive this many-modal work? And secondly, how we can design how we can method world to leverage those information effectively. So this might be a little bit not intuitive, but actually with believed to a very strong multimodal baseline, it cannot adapt new modality very effectively. Like in our early experiment, we find that on some designed audio-video QA task, when we are trying to adding more information into this framework, it actually leads to a decreased performance. So this highlights the challenges behind the incorporating many-modality learning in current multimodal large language model systems. So in this work, we propose a CREMA. So CREMA actually contains two parts. So one is the model side and another is the training optimization side. So I will first go with the model side. So, giving a many-modal world with many different modality like video, depth or depth map, optical flow, audio, 3D point cloud. We will first use a modality-specific encoder to map them into a specific space to be embedding before we put into the large language model. But the problem is that we need first to map this different modality information at different space into a unified language model space to let the language model can understand them. So that's why we decided to use a multimodal Q-former. So here comes the problem. If we are trying to train an independent connector or this so-called multimodal Q-former for each modality, this will lead to the very increased trainable parameter, so which is not that efficient. So our solution is that we will share the Q-former backbone, but only insert the LoRa part, which is technical for the hyperparameter efficient fine tuning. So we will insert the modality-specific LoRa to each modality. So during the fine tuning, only this part, a small part of parameter, are updated to adopt this new modality. So with this multimodal Q-former design, we share the Q-former backbone with very limited trainable parameter to map the different modalities information into a unified space. But here comes the next problem. So actually, not all modality or all extra modality beyond the visual is very useful because those modalities sometimes are estimated by some models, so they have some lower quality. So the problem is that we need to compress this modalities information to make to extract the useful part, but discard the unuseful part to let the model can be more effectively and efficiently leverage these informations. So here we propose a very simple solution where we will merge those extra modality information with self-gated fusion. So which means we will first concatenate all those modality tokens together, and then we will put them into a fusion model. And then we will apply a self-gated fusion, which is actually a rule-based filtering method that controlled by a sigmoid function. So this is very lightweight, so this will not introduce many hyperparameters. But in this case, we can place this self-gating as a filtering function that can filter out some unuseful information, but remains the useful information for the downstream task. So in this case, we will have the video modality and the few many other modality information that can be useful for the downstream tasks. So this that is a model side of the CREMA framework. So actually, we in our project we also observe that there are many difficulties in the optimization multimodal work, because previously we just trained it together, but we just find that actually this is not work when we trying to optimize all those modalities module together. because some of the reasoning behind this is that varying the quality of information across different modalities. So when we're trying to optimize them together, it's always lead to a suboptimal convergency. So here we propose a modality-adaptive early existing strategy. So let's give this figure as an example. Let's assume that we have 4 different modality: text, video, 3D, and thermal heat map, and they're starting from some initial stage. So actually, we will determine early stop indicator, which is determined by the gradient of the attitude of a gradient during the training. So this is a rule-based indicator, and we set a hyperparameter to control this existing threshold. That means, let's say when the epoch training to be 8, and we find that, okay, the gradient of this model updating is saturated. So that means this model can, our CREMA model cannot be benefit from this modality anymore. So we will stop it. So we keep the lower part of this modality locked or frozen. So it will be fixed to exist from the training. And when the training process goes, and we will find that more modality become converged. So more modality will stop the updating. So the whole process, training process, will end when all modalities are existing from the training. So actually, this modality-adaptive early exist strategy helps not only on the performance side, but also on the efficiency side, because we don't need to wait the every modality trained at the end of epoch, but they can self-adaptively to decide when to stop. So this brings us a more fast convergencing of the model. So here we comes for some experimental comparison with some baseline model. So we can see that with some previous model like BLIP2, they're actually struggling for incorporating more modalities. Like it will decrease the performance when we are trying to adding new optical flow information, which is not intuitive because we're already providing them more information, but they cannot take use of this. But our CREMA can be keep increasing the performance even we are adding new modality, more new modality, like we're adding depth map and the surface normalization. So this brings us more and more increased performance. And another important part is that at the same time, because CREMA adopt modular training, so there is just a very few part of extra parameter introduced in the training. So compared with BLIP2, the trainable parameters increase dramatically. CREMA can maintain the trainable parameter very friendly in size. So this is important when we want to apply this model very fast, very efficiently to some domain-specific things. So actually, we test our model not only on the audio video QA, but we actually tested very densely on 7 different benchmark over 11 different modalities. So we have a 3D QA, 3D video QA, and we have a standard video QA, which is assessing by some flow, depth, and normalization. We also have some real modality QA like touch map and the thermal heat map QA. And we will always say that CREMA's framework and training strategy helps the model improves to a better performance while keep a relatively small trainable parameter, which is more efficient. So here we go to some qualitative analysis. We can see that in CREMA framework, when we're asking the question, is the first sound coming from the middle instrument, where the answer is no, the GT answer is no. But when the input map is only audio plus video, the model sometimes will be hallucinated and they will generate some wrong answers. But with considering with optical flow map, this kind of information actually provides some precise motion information. So the model can be helped from those information to infer that, okay, there's no obvious signal in the optical flow. So that means there's no motions in the middle. So the model can tell that, okay, the middle person is not moving. So the first sound is less likely to comes from the middle instrument. So that's why CREMA works from a qualitative views. So yes, I think that is the presentation for our CREMA work. Thanks for attention, and any questions?
Awesome. I think we just right on time. So yeah, thanks again, Shoubin, for going over this awesome work. I think you mentioned here that you currently incorporate a variety of modalities, right? From videos and optical flow to audio and 3D plotting.
Yes.
Are there any other modalities that on your radar that you're curious to explore?
I think must be some medical domains, because actually this medical analysis, they are the things, application things that require many modalities to help the doctor to to analyze the disease. So I mean, extending the CREMA framework to some medical domain is actually something I'm working on, because we have the text is a medical report, and we have some borrowing CT scan, and we also have some some other modality other medical modality information. So yeah, like just like doctors seeing a patient, they are actually collecting information from those different things. So we want to create a framework plays like this role. Yeah.
Very, very cool. I guess the multimodal, just kind of going back to draw figure overview, the architecture, the multimodal encoders in this scenario need to accept it as input like all the modalities, right? What is the choice of encoder that you use for the experiment?
Yeah, it's modality specific. So each different modality, they will have their pre-trained encoder. Yeah, pre-trained encoder. Like for yeah, for audio, we will have a pre-trained audio encoder. For 3D, we will have pre-trained 3D encoder. But for some real modalities, like optical flow depth map, we will share with the view encoder.
Yeah, I'm curious, like which encoder it is. Is it open source?
Oh, it's VIT.
Say it again?
It's VIT, that transformer. It's VIT, yeah.
Oh, read it from Google. Is that the
Yes.
one? And like once you got these separate encoders, how do you merge them together into? Oh no, so you have different encoders, right?
Yeah.
And for each of the output of the encoders, you're gonna feed that into the Q-former layer.
Yeah. And the fusion actually happens after the Q-former before sending into the LLM. Yeah.
I see. So you did the fusion. Now, the purpose of the Q-former is to extract the token for each
Exactly.
modalities.
The
And then
Q-former is used for, to compress these tokens from the encoder. Yeah.
yeah. And the challenge is here, like what if like the tokens from each modalities have different dimension? Like how do you
Oh,
this
that linear projection to mapping them into the same dimension.
oh I
Yeah.
see. Yeah, got it. Pretty- Okay, awesome. Super exciting work here. Yeah, I think C was telling us earlier that you also have another work coming up, right? Would you
Yeah.
mind quickly talking about it?
Yeah. It's a video tree. Sorry, I may not have slides for this, but
No,
maybe I can
no.
share some squaring. So we haven't announced this, but this has been accepted by this year's CVPR.
Mhm.
So yeah, I think the major idea, we'll just get a quick overview of this. So it's an advanced version of LLoVi, but the problem of the LLoVi is that it still not capture some query-related moment. But we are actually building a train structure strategy that used for the keyframe selection. So this can help us to use a cross-define strategy to locate which moment might be related to the query. So we will use a list frame, but achieves the higher performance. Yeah.
Awesome. Okay. Well, thanks, Shoubin, for presenting and closing up the webinar. So I know we got a couple minutes over time, so I want to do the concluding remarks. So yeah, appreciate you guys coming in and giving talks at our session. The recording should be available within the next couple of days, so be sure to share it here, and we can promote it within the research community. Overall, like super relevant work in video language modeling, video understanding. That obviously is super relevant to tutorial labs. So yeah, excited to see how the field is going, especially like with some of the things with reasoning capabilities of LLMs. I think there's a lot of advancement that we can incorporate that to the field of video foundation models, right? And for the attendees, thanks again for attending today. And we'll have a lot more interesting webinar session like this over the upcoming weeks. So be sure to return and check it out.
Cool. Thank
All
you,
right.
James. Thank you for holding this event. Thank you.
Right.
Thank you.
Thanks, guy. I appreciate it.
Cool. See you.
Bye.
Let me stop recording.